Okay, so let's get into what really should be the fun stuff in the class. And so I want to start out by showing you the Hello World project for an embedded controller, and you know, the little controller, the little chip there you see in the lower right hand corner of the screen. There's no keyboard, right? There's no monitor. So instead of Hello World, which is the traditional first program you make, we'll make an LED blink. All right, so that's what we're going to do first. And I'm going to start out with this code that you won't yet understand. I mean, you'll recognize it as C code, but the specifics of it won't make sense to you yet. We'll look at the code in just a bit, but first I wanted to show you on slide 2. There are a couple of things I want you to notice. First of all, you'll note that you get these little red squiggles here. That's because Visual Studio Code says, I don't know where these files are. AVR/IO.h and util/delay.h. These are codes that come with the library for a different compiler and a different tool chain. It's the AVR GCC tool chain. And so I just wanted to use this occasion to make clear, you know, previously you were using the GCC compiler, and it was either the CLang version on your Mac or it was the Min GW64 on your Windows machine. Those are both implementations of the GCC compiler, which stands for the GNU C compiler. Those are compilers that take your code and then they compile it down to the processor that runs your laptop. And most of your laptops actually have the same processor machine code, whether it's a Mac or a Windows machine. They all tend to have the Intel x86 micro machine language in them. And so those compilers take your C code and they compile it down so it's understandable to the microprocessor in your laptop. That's what we've been doing so far, unless you were using this online GDB compiler. Now we're doing something different compilers. So you can delete those previous compilers if you want to get that space back. What you want to do now is download what's called the AVR GCC compiler. AVR is the name of the processor in the family of microcontrollers we're using. And you'll learn more about that as time goes on. And so you need to download what's called the tool chain. It's the compiler and it's a set of other utilities for ultimately getting C code like this translated into machine language understandable by the microcontroller. And we'll talk about all that today and Wednesday and so forth. But I just wanted to point out that right now Visual Code was set up with the C/C++ extension, and it doesn't understand the AVR GCC compiler and the set of libraries. And so at some point we'll fix that, but right now what's happening is it sees these and it says, I don't know what these files are, so it's just going to give us a squiggle. Okay. The other thing I want you to notice is over here, you know, if you're looking at the Explorer view here in Visual Studio Code, there are 2 files here that are important. There's one called BlinkC, that's the source code. I'm going to show you about that in more detail on the next slide. There's also a file there called a makefile. And from now on, every time you make a program in the class, you're going to have with it a makefile. And a makefile is you can think of it as kind of like a macro. It helps you do all the steps that are needed to compile and then download that source code onto your microcontroller. So you'll be seeing these make files a lot. Okay, so now let's just take a look at the code itself. Okay, what's it doing? Here's the block comment just tells you about it. We're going to blink an LED on port B pin 5, also known as PB5. We'll get into that on Wednesday. All right, and this happens to be the built-in LED on the Arduino Uno. Okay, so what's happening? We first have these preprocessor directives. We're including some stuff. We'll get into that on Wednesday. Then we get into the main function here. And what's it going to do? It's this first line here is just saying that I want to set one of the pins on this microcontroller as an output pin. And then what I'm going to do down here is I'm going to make that output pin go high. Here I'm going to wait. I have a delay. I'm running a built-in function that comes with this this installation of C, and the function is called myDelay in milliseconds. I'm going to specify a delay, and that value of that delay is coming from here. I'm setting it to 1,000. So what I'm going to do in this program is I've got a while loop. First of all, notice the while loop. It's while 1, right? 1 is always true. So this is an infinite loop. It's going to loop forever. And this is the standard way that we write a lot of these codes, because, you know, when you've got an application running on one of these microcontrollers, it's unattended. You just set it running and then you leave it alone, and it just keeps on looping. It keeps doing the same thing over and over again. So we have a while loop. The contents of that while loop, we're going to set a bit high. That is, we're going to set one of these pins high, and I'm going to connect an LED to it so that it blinks. Then we're going to wait, and we're going to wait 1,000 milliseconds, which is a second. Then we're going to set that pin low. The LED will go off. We're going to wait 1,000 milliseconds, and then we're going to loop again. Okay, so that's the code. It doesn't make sense to you at this point other than, yeah, this looks like C code. It'll make more sense on Wednesday and subsequent days. Okay, let's suppose we've written that code. What I want to do now is I want to compile it. But I want to compile it not for the microprocessor on my laptop. I actually want to cross-compile it. I want to compile it so it's understandable in the machine language of the tiny little microcontroller. And then we have to download it to that microcontroller. So previously, the way we compiled is we just did GCC, and then we had the name of the output file, and then the name of the source code. Okay, here, take a look at this first line. This is what I have to type in here to compile this thing. So the code is called blink.c. So I'm specifying AVRGCC instead of GCC. It's a different compiler. Okay. All of these things we'll get to. Here I have to specify compile this so that it can run on an ATmega328P, because there are dozens and dozens of different microcontrollers. Here we need to specify, we want this to be cross-compiled into the language that's understandable by the ATmega328P. That's the particular processor we're going to use, okay? We have to tell it, the processor we're using has a clock on it that's running at 16 megahertz. You see, computers don't know time. They just know how many times something has happened, right? Computers, the way they keep track of time is they count something. You know, they might do something 1 time or 1,000 times or 1,000,000 times. That's how it sort of sets up a delay. You have to tell it what's the duration of each clock cycle so that it can, once you tell it the duration of the clock cycle, it can figure out how many cycles or how many iterations it has to undergo to achieve a delay. So we have to tell it we're using a 16 megahertz clock here, okay? So I have to type in all of that kind of stuff, and then I have to do this other thing called AVR object copy. Okay, what's all this about? Don't try to understand it right now. Just hear it, let it wash over you, all right? So some points. We're using the AVR GCC compiler for these microcontrollers, right? And we need to specify the target microcontroller. Compile this for that particular chip. And we have to tell it the clock speed, because you can run these chips at different speeds. After we're done compiling, I have to create what's called a hex file that has the binary instructions for the microcontroller, right? 1s and 0s, because microcontrollers think in 1s and 0s. But the way you actually download that is with a hex file. So I have to create this hex file for this really should say downloading. Some people are not precise about when are you downloading and when are you uploading. You know, and so if what we're going to do is we're going to take this code, we're going to cross compile it, we're going to represent it in machine language, and then we're going to turn it into a hex file, which is just a hexadecimal version of a pattern of 1s and 0s. Then we have to transfer that to that chip. Are we uploading it or are we downloading it? Some people would say uploading, some people would say downloading. Usually what's meant there is when you go from a bigger machine to a to a smaller machine, right? When you're getting something from a bigger machine, you would call that downloading. So, like if you download something from the internet, or you upload something to the internet, right? You're going to a bigger machine, right? So more on that later on. But the point is, we have to create something called a hex file that we can then use to port this code over to the microcontroller. So I want to show you what happens after I execute these statements, right? The thing to notice about these two statements is that they're kind of complicated. There are a lot of things I had to type to execute those two statements, right? I had to do the AVR GCC, something called OS, something called wall, specify the microcontroller, specify the clock. Yeah, it's a lot of typing that you have to do, right? Once that's done, I want you to notice, and when you do this, what you will see is you will have what used to be 4 files. There are now, used to be 2 files. There are now 4. There are 2 additional files that were created. One is called the object file. That was the result of compiling. And the other one is this hex file. And I'm going to show you that next. Okay. Here's that hex file. What this hex file represents is the hexadecimal version of all of the binary instructions for the ATmega328P chip, right? That will run this this program to blink an LED. So this is the hex formatted version of the compiled executable binary code. We started out with our source code. We compiled that. We told it compile it for an ATmega328P microcontroller, right, at 16 megahertz, and create this hex file. And the next thing we're going to do is we're going to download that to the ROM on the chip itself. Okay, so we now, and you obviously couldn't program this way, right? I mean, it would be ridiculous to try to program like this. That's programming in machine language. You could program in assembly language, which is closer to this. But what we find is when we program in C language, which is higher level than assembly language, it's a lot easier than doing it in assembly language. And the result is this product, which we'll then download to our chip. Okay, how do we download it to the chip? It's this command here. Okay, there are a bunch of things that have to get specified. So first of all, we're running a program called AVRdude. AVR is the processor on the chip. AVRdude stands for AVR Download Uploader. That's the people that sort of created this came up with that name. AVR Downloader Uploader, AVRdude. Okay. Okay, we're going to be using initially an Arduino board as our platform. We're using a baud rate of 115,200 bits per second. This is the communication port that my Arduino is connected to. And so once I type all this, then you're going to see all of this kind of stuff here, right? And what it's doing is it's taking the code, that hexadecimal pattern, and it's storing that, it's downloading that to the flash RAM on board the device. And when we're done, it'll look like this. Here's the Arduino board. It's connected to power here. We've flashed this device. Okay, let's see. And it's going to blink. We're blinking, and the internal LED on for a second, off for a second, on for a second, off for a second. Okay, so that's simple, right? So that's Hello World, is just getting the internal LED on the Arduino to blink using real ANSI C code and compiled this way, right? Now you may have done this sort of thing before using Arduino scripting language. We're not doing that. We're writing C code, compiling it, and then downloading it. Now, let me back that up. You just notice notice that blink rate here, right? It's blinking on for a second, off for a second, on for a second, off for a second. Okay, suppose I want to make it blink faster. So I'm just going to go and I'm going to modify the code ever so slightly. I'm just going to change this delay from 1,000. It was 1,000. I'm going to make it 100. that's 100 milliseconds. So now what it'll do is it'll turn on the LED and it'll be on for 100 milliseconds, a tenth of a second. Then it'll turn it off and it'll wait for another 100 milliseconds, a tenth of a second. So it'll be much faster. So instead of on, off, it'll be on, off, on, off, on, off, on, off, right? Much faster. Okay. So we changed the code. Now we have to go and recompile it, and then we have to download it again. We have to flash the microcontroller ROM again. So that means going back and retyping all of those compile commands, right? Instead, all I do is I type the word make. And what make will do, make is it's a funny name for a program, but this is actually an executable program. And what this will do is it will read a file called makefile, and that will automate that whole process of compiling for us. So once you type make, all of this stuff happens. So you can sort of think about this as being a like a macro, right? It sort of automates all this for you. And when you're done with make, what happens is your source code has been compiled and it's now ready to be flashed to the ROM on the device. So now to flash it to the ROM on the device, previously we used AVRdude. Here you just type make flash, and that will actually call up AVRdude for you. And when that's done, that will result in a new compiled code being flashed to the device, and you'll see it's blinking a lot faster. Okay, so every time you want to change it, what you do is you change your source code, and then you just rerun the make file, make and then make flash, and that'll compile it, and then that will then download it for you. So I just wanted to compare the two different ways we did this. On the left is sort of the difficult way, where we had to type everything in at the command line. I had to type AVR, GCC, and all this other stuff, right? I had to do AVR object copy, AVRdude, type in all that. Or on the right side, I just did make followed by make flash. Okay, and that simplified it. So we're going to be using a make file to automate that for us. Okay, and this is what that make file looks like. Now, every time you, going forward, every time you start a new project, right? Think about it as a new program, right? Don't think about it as a program. Think about it as a project. And the reason why you want to think about it as a project is there's both hardware and software here, clearly, right? And a program just implies software. So when you start up a new sort of, endeavor here in the class, think about it as a project, combination of hardware and software, and create a folder or a subdirectory for that project. And the reason why you need to do that is you're going to have your source code, which will be in one or more files. You're also going to have this make file that's in there. And that's the file that will automate this compile, object copy, and then AVRdude process. And so you'll find this file on the week 4 tab of Moodle. And what you want to do is every time you start up a new project, just take this file and copy it into that folder. The instructions are there on what you have to do. All you have to do is just change 2 things every time you have a new project. One of them is just the name of the source code file. I called it blink.c, and you'll have a new project. You'll probably have a different name for the source code. So you just put that there. Also, depending on where you plug the Arduino into your computer, it might show up in a different COM port if you're using a Windows machine. It could be COM1, COM2, COM3, 4, 5, 6, or whatever. If you're using a Mac, it's going to show up as a different USB modem port. So you have to find out which is the right port, and you just specify that there. And then the make file will automate that compilation and uploading process for you. Okay, so that was just a quick look, and we're going to see all this again repeatedly starting now. That was all. How do we make a blinking LED using the Arduino Uno? Okay, and why did we use an Arduino Uno? Okay, well,
Professor,
yes,
a question in the room.
Okay.
What is main.l?
What is main.l mean?
ELF.
Oh, ELM.
What is main.elf? Main.elf was the name of what's called the object file. And we're going to go through this in more detail later on. It's not something you have to worry about right now, but it's an intermediate product. After you compile, there's what's called an object file. That object file has to get linked with other object files, and then it has to get turned into a hex file. That's all the internal machinery of the compilation process. And we'll say more about it later on. For now, you don't even have to know about it. For now, if you just run the make file, it'll take care of it for you. Okay, let me see. I had a couple of questions here in chat here I wanted to get to. Someone asked, are we still doing C language or are we doing the Arduino language? I'm glad you asked the question. We're using C. We're going to stay within ANSI C for the entire course. We won't write any Arduino code. And for those of you, those of you who are familiar with Arduino know that, when we say Arduino, what do we mean? There's a piece of hardware. It's an Arduino board, and I'm going to show you that in a bit. We looked at it once, but I'm going to show you why we're using it. There's also the Arduino IDE, the Integrated Development Environment, and there's the Arduino scripting language. It's a variant of C. It really hides a lot of the details from you. We're not using that. All we're using from Arduino land is parts of the IDE, and we're using the hardware itself. So we're not using the Arduino scripting language. Okay. All right. What I did is I showed you what it looked like when we took some code and then we flashed it to the ROM, the flash ROM on an Arduino Uno. We flashed it to the ROM on the ATmega328P chip, which is residing on the Arduino Uno. Why are we using an Arduino Uno, right? Why aren't we just using the chip itself? Well, let's take a look at what would be involved in putting code on a bare chip. We're talking about a bare integrated circuit chip, right? Nothing else on it, just the chip. So that's what's shown here. Think about this as this, this is your, this is your 28-pin, what's called a plastic dual inline package integrated circuit chip, right? So it's an IC chip that has 28 pins on it. You can push it into your breadboard. You're going to have one of these in your kit. Now, if we wanted to make an LED on this blink, right? Well, we could take our LED and we could hook it up to one of the pins, right? We're hooking it up to pin PB5. That's fine. We have to then power up this chip. It wants 5 volts. So we might get a 9-volt battery and a 5-volt regulator to give us 5 volts. We'd have to get an external crystal so that the chip is clocked at a certain frequency. We have to sort of put all this provisioning on there, all the circuitry just to make the chip go. Then we would have to get a piece of hardware called a programmer. That actually is the hardware interface, hardware and software interface between your laptop and the chip itself, and it serves to actually accommodate the downloading process. So this is I showed you this on the very first day of class. This is what we'd have to go through if we wanted to cause the LED on there to blink. I have to upload code using that white box. Okay, now the LED is blinking. I'm going to pull away this programmer. Okay, and there's the end result. We now have that code, that same code I just showed you, flashed to the ROM on this device, and it's embedded there, and it'll run as long as we keep the power applied to it. So this kind of thing, a bare chip, a bare integrated circuit chip on a breadboard is our target for this class. That's the kind of thing that we're after. That's what we're going to mostly be doing. And in a few weeks, we'll be building things that look like this. All right, that's one of those chips on a breadboard. This is an ultrasound sensor. It's a little sonar sensor. And what this board is configured to do is to detect objects that are within a few meters away. And if they're less than 1 meter, cause this LED to turn on. So it's a close distance object detector. And we'll be building things like this pretty soon. Now, to build this, you need to give it a crystal. and you need some capacitors for it, and you need a voltage regulator. You don't need it, but you can put an LED on to tell you the voltage regulator is working. And so you need a fair bit of support circuitry just to make a chip like this on a breadboard work. Okay, now I'm gonna come back to this in a minute, but before I do, I want to show you the difference between developing code and developing an embedded project using just a chip on a breadboard versus using the Arduino Uno. But before we do that, I want to just digress a little bit and talk about these chips. Okay, so I want to talk about the AVR family of microcontrollers. All right, AVR is the family of microcontrollers we're using. The processor inside all of them is the AVR. I'm going to show you some block diagrams, a little bit about the development boards, a little bit about our programming environment. Okay, on day one of the class, I told you this is the textbook for the class, and you should read sections 7.1 through 7.3. Now, this book, you can get the Kindle edition if you're comfortable reading that for only $15 from Amazon, or you can get the paperback, whatever you're more comfortable with. This book covers programming of our chip using both assembly language and C. Assembly language is in the first half of the book, C is in the second half, and that's why we're starting here with sections chapter 7, 1, 2, and 3. You can skim through those earlier sections if you want, particularly chapter 1, but that's mostly about assembly language programming. Okay, so about these chips, okay? Whoop. All right, peace. Here is our chip. This is the chip we're going to be programming all semester long, right? It's a small chip. It's just over 3 centimeters long, okay? Now, what's inside that chip? Well, what's inside is a whole bunch of transistors. That's how we make chips, right? We're not going to really worry about what's literally inside it, but in terms of a functional diagram of the inside of that, you can think about it like this. This is a simplified view of what's in there, okay? So there's a program flash ROM, flash read-only memory, right? It's like a flash drive that you have on your computer. And this is where when we compile code and we upload it like we just did, right? We're flashing it to the ROM on this chip. All right, now this chip has a number of other things. It has RAM, which is where it's storing variables. It has an electrically erasable, programmable read-only memory. It's a kind of a ROM, but you can erase it. It will store things after the power is taken away. It has some timers and other peripherals, but I'm going to focus just now on these ports, these I/O ports. And the I/O ports are the pins on this chip that we can cause those pins to go high or low. High meaning those pins have 5 volts on them, low meaning 0 volts. If it's 5 volts, we'll cause an LED to glow. If it's 0 volts, it won't glow. Okay, so we're going to focus on the pins. And I wanted to show you this. I'm going to go back a slide. I'm going to just jump back to the one I just showed you. This is a very simplified view of the architecture of any of these AVR chips. On the next slide, this comes from the data sheet for our chip, the ATmega328P chip. And this is the way the manufacturer describes the architecture of the chip. This is a more detailed version of the simplified architecture from the previous slide. There's a whole lot of stuff on there, okay? All I want you to do is concentrate on what's on the bottom in the red oval here, right? And this is where the chip interacts with the physical world. It has these ports, port D, port B, and port C. And so this chip is characterized over here on the right as having 23 general purpose input-output pins, or GPIO pins. They're in 3 different ports, port B, port D, and port C. And it turns out ports B and D have 8 pins and port C has 7 pins. So there are 23 of them. So these are 23 pins on this chip that you can set high or low, or you can read them, and you can read if they are set high or low by the external world. And this is one of the key means by which one of these chips interacts with the physical world. And so what we've been doing so far is just taking one of those pins, PB5, and we've been setting it high or low and connecting an LED to it. Okay. Okay. A couple other things on here. In addition to the GPIO pins, there are these other, they're called peripherals. There's analog to digital converter pins. There are some timers. There's a UART or a USART, but it's called a USART, but we only use it as a UART. More on that later for communicating. Okay. This chip has on it 32 kilobytes of flash ROM. Okay, that's where it's called a 328. That's where the 32 comes from. It's the fact that this has 32 kilobytes of flash ROM. So the this little piece of code that we wrote to blink an LED, that takes up 180 bytes. You can write code up here that goes up to 32 kilobytes, right? Still tiny compared to, you know, the amount of storage space you have on your laptop, but it's enough for what we need. Okay, just one more thing before I move off this chip. You can buy them for a few bucks, and it comes in different packages. You can get them in packages that need to be mounted in special ways on circuit boards. For example, they need to be surface mounted. They can't plug into breadboards, or you can get the version that we've got that plugs into a breadboard. It's called a PDIP, plastic dual inline package. Called plastic, it's a plastic package. Dual inline package. Dual inline refers to the fact that you have the chip has 28 pins, and they're in one row of 14 pins and another row of 14 pins, and they're in line, okay? As opposed to one of these others, the quad flat package. It's where this is dual, it has 2 rows of chips. The quad package has 4 rows of pins, okay? We're gonna be focusing on the dip because we can push those into a breadboard. Okay, question is, if you have a 328P, but it has the Arduino bootloader burned on it, will our code be able to run on it? We'll end up wiping, we would end up wiping the bootloader off of it. One of the things we'll be getting to later on is things like dealing with the clock speed of one of these, dealing with whether or not the chip has a bootloader, and then dealing with the fuse bits, which are used to change certain things like the clock speed on it. You have to really be careful if you at this point, if you don't know what you're doing and you start to mess around with the fuse bits on one of these chips, it's very easy to brick it. It's very easy to get it to a point where you can't access it anymore. So this questions of bootloaders, fuse bits, changing the clock, we'll get to those, but later on. All right, I'm going to go to the next slide. I just want to show you a different chip from the AVR family. We're looking at the ATmega328P chip, right? For our purposes, it's a 28-pin chip, right? Okay, here's another one, the ATtiny microcontroller. So it's tiny because it's a smaller chip, right? It only has 8 pins on it. So it's an 8-pin package, and it costs less, right? I'm going to jump back to the previous slide. Our chip costs about $3.50. You can get these for $1.19. All right. Okay. Well, it's a tiny chip, so sometimes it's better to work with a chip that doesn't take up as much real estate. It also doesn't draw as much power. This one only has one I/O port, port B, and it has 6 pins on it. So this one only has 6 general purpose input/output pins. And it has fewer analog to digital converter pins. So it's just another chip that's smaller and less capable than the 328P. Okay, these are some tables from your textbook, and they just compare some of the dozens and dozens of variants of AVR chips. And so there's the ATtiny, those are the small ones. There's the ATmega, that's the series that we're working with. Okay, you've got some of these chips have 8 pins. Okay, ours is 28 pins, right? All right, that's the one we're working with. Our 28-pin chip, it actually is pretty big. I mean, it's a fairly large chip. at least in comparison to the size of, say, a cardiac pacemaker, right? It's an awfully big chip in comparison to something like that. But you can get these chips that go all the way up to 100 pins, right? So that's a much bigger chip if it's got 100 pins on it. Okay. Why do you need more pins? What's the deal with the different peripherals? How do we use them? That's what we're going to spend the rest of the course learning about. So this is a slide that I showed you at the very beginning of class. Embedded programming, what this whole thing is about, is that we're going to be reading and writing to memory locations, right? Also called registers, in the I/O interface of these chips, right? In the GPIO interface. We're going to be reading and writing to special purpose registers at those interfaces. And we'll be doing that to set pins high or low, or to read whether pins are high or low. That's one way for us to interact with the world. We'll also be configuring what are called the peripherals, the timers, analog to digital converters, right? And we'll be using C constructs, loops and conditional branching, the stuff we talked about over the past couple of weeks, to put together applications. Okay, how do you do it? What's the hardware look like? Well, these are 4 different ways we can actually implement one of these chips. So we can get on the lower left, we can get the bare chip here, right? We can write our code and we can put it on it. And if we're running on a breadboard like this, we have to give it a clock. So it'll run at a certain speed. We have to give it a certain voltage. So that often means we put a voltage regulator on there. And we have to just provide some basic provisioning for it. That's what it looks like on a breadboard. Up here on the top right, this is what it looks like on sort of a custom development board that I made for my own purposes. And this is a board where everything is soldered in, and I have that crystal and I have that voltage regulator all sort of soldered in on the board. And the difference between these two, the one on the top right, you can think about as a development board. I made this, I can pull this chip on and off easily, and I can use that to program different chips. And it has all this hardware stuff built into the board I made. Now, commercially, there's a development board called the Microchip Explained Mini. This is the board we used in this class last year. This is the chip. It has one of these quad surface mount chips instead of the dip chip. But it also has other things on it, like a clock. I think this is the clock, right? And it also has voltage regulators and things on it. And another version of a development board that we're using is the Arduino Uno. So the Arduino Uno has the chip on it, right? It also has a clock on it, and it also has voltage regulators on it. So however you work with one of these, you've got your chip, you've got to have it on a board, you have to provide the right kind of voltage, so that means voltage regulators typically. You have to provide clock crystals and things like that. Soon, we want to get to the point where we're doing this. But rather than have you start with a bare breadboard and a bare chip and have you have to worry about clocks and everything else, we're starting with the Arduino Uno development board, because that has a lot of that provisioning taken care of. So we'll start out with this. We'll spend 5 weeks using the Arduino Uno. We're programming the chip in ANSI C, the stuff we've been learning about. We're programming the chips using the Arduino as our development platform. We'll be connecting the Arduino to the outside world using these headers here. We're going to be sticking wires into these headers, these sockets, right? But that simplifies the task. We don't have to worry about putting a clock and putting other things on there, okay? So that's how we start. Just so you'll know, there are different flavors of Arduino Uno. Well, first of all, there's a lot of different Arduino boards. We're using the Arduino Uno board. And even when you talk about the Arduino, question?
I did not see a question.
Okay. Let's see. Okay. Yeah. So someone asked the question, if we have the Arduino that has a bootloader burned on it, will we have a problem? No. No. The way we will actually be programming the Arduino is we will be making use of the bootloader, and so we don't have to worry about that. That will be invisible to us. So this is many things about the Arduino are going to be invisible to us. So for example, we're not going to concern ourselves with the details of what all of this stuff is. Some of it we'll get into, but there's a lot of functionality on here that we're simply we're going to ignore. We're going to take for granted that it works. Likewise, the way we actually program it, we're going to allow Make to take care of that. And we have a specification in our make file that will allow us to program the Arduino Uno making use of its bootloader. Now, if you don't know what that means, don't worry about it for now, okay? I just want you to see on this slide that there are lots of Arduino clones out there. There's the Velamin, and they're the same. The Arduino Uno, the original one, and the Velamin are the same. They're identical. One's a clone of the other. There's also SparkFun makes a red board, which is it's not an exact clone, it's a quasi-clone. You have to actually download some drivers to make the red board work, and the connection on it is a little bit different between that and these others. We're going to be using the Arduino Uno. Okay, so that's what we'll be using for the next 5 weeks. Now, what's the relationship between the Arduino Uno, the device we're going to use as our development board, and the chip? Well, here's the chip, and you can see all of its pins. And then this drawing here shows you the correspondence between the ports that we're going to care about, right, and the pins on the Arduino. Okay, so we'll be making use of this figure a lot. If we want, let's suppose we want to put an LED on PB5. Okay, I put an LED on there. All right, and I need a resistor there, and then a ground, right? Well, it was a terrible drawing. But if I wanted to do the same thing with the Arduino Uno, I would connect it to this pin over here. The difficulty I'm having is I have a right-handed mouse and I'm left-handed, and I can't quite make it work to draw. I can draw simple lines, but I can't draw anything more carefully. The only point about this slide is anything that you want to access on the chip, you can also access on the Arduino Uno just using this pin correspondence. Okay. Okay, I'm getting close to wrapping things up here. I just wanted to tell you just some principles, some rules of thumb about the kind of programming that we're doing. We're doing what's called bare metal programming. I mean, there's no operating system involved. We're running a little tiny chip on a board with a clock and a voltage regulator, but there's no room for an operating system. So the entire operating system is the code that we write, right? You can think about it as firmware, the code that we create, and then we flash onto this. That becomes the app or the operating system that runs the entire chip. Okay, so that's what we're dealing with here. Compiled high-level code, we write it in C, we flash it to the device, and it's embedded there. We're starting out in C. And it turns out it's quite straightforward. If you wanted to make this code run on a different chip, you may recall early when we started to compile this, I specified after AVR GCC, I specified that we wanted to compile it for the ATmega328P chip. If you want to compile it for a different chip, you would just specify that there. So you could specify that in your make file. So it's straightforward to port the code from one chip to another one. Okay. These are devices that have a small flash ROM and small RAM space. So we're going to have to keep track of how much space our different variables and our arrays are taking up. We'll be dealing with fairly small programs. We're going to learn about register level programming, which means that we're getting close to the hardware. We're going to have to really get down to the point where we're writing code that are going to turn individual bits high and low. And those bits are located in registers, and we're going to have to learn about the different registers. So a lot of bit level manipulations, bit twiddling, making bits go high or low. All right, headless, there's no monitor and display and no keyboard typically, although sometimes we will using the serial interface on this device and a USB converter, we will connect back to our laptop, and we want to send the data over the serial communication port so it shows up on the laptop. Okay, we're going to tend to use more global variables than you see in typical C code, and we're going to use what's called super loops, and I'll show you what that is next. All right, now, if this stuff doesn't make sense to you, don't worry, it will over time. I just want to show you the basic architecture of what some people call the super loop. This is what most of the programs are going to look like. Okay, so by now you've seen enough C. You can look at this. You can say, okay, I recognize that. That's my main C function. Okay, and what we'll often see is we'll write code that looks like this. We'll have a function, an initial function that will initialize something. It's going to go and set up something. It's going to set up an A to D converter, set up a communication link. It's going to, but some function that we create or we call, it'll set things up. Then we're just going to get into this loop. And the basic operation is, while one is always true. So this while loop is always true. So this will keep on running. Once this loop starts, it's an endless loop. It'll run forever. And that's the standard programming paradigm for a microcontroller, is it's just doing stuff inside an infinite while loop. Now, there may be occasions when you want to put it to sleep and then wake up. It'll wake up if someone bothers it. If there's a vibration sensor it picks up, it'll cause it to wake up, but that would still happen within this while loop. What happens within the while loop? We might do something, which is some task, do something else, which is another task. Those are both functions that we create. But this is what the picture looks like, sort of the overall architecture of the super loop. All right. The slides 29 and 30 and 31 and 32. I encourage you to just read those. I'm not going to go over them. They're sort of some look ahead kind of stuff. All they are is they're just a particular instance of this. I just told you generally what this super loop architecture looks like. And on slide 29 is an example of one of those. It won't make any sense to you, but I'd like you to just sort of see what the structure of it looks like. And then slide 30 is when we take that and we rewrite it with functions 2 different ways. All right, so take a look at those and read this observations on your own, okay? And I want to just tell you about lab assignment 2, and then I want to get into talking about kits. All right, so lab assignment 2 is assigned now. It's due in 2 weeks. So the first thing you have to do is you have to install your tool chain, the AVR GCC tool chain. And so you're going to go to this link. This is a website at University of Southern California, and this is courtesy of Professor Redicoop there with permission from them. Let me just say briefly what's going on here. So to install this AVR GCC toolchain, if you're on a Windows machine, it's easy. You'll just install it and it'll go. It'll be straightforward. And the thing about it is it's usually the tool chains that you find are 32-bit tool chains. Ever since Mac OS introduced Catalina, so Catalina, Big Sur, and now Monterey, those operating systems will only run a 64-bit application. So to go out and find an AVR GCC tool chain that runs 64 bits, the easiest way to do it is to reach into the Arduino IDE and pull some of the guts of that out and install that. And that's how you can get a 64-bit version of the AVR GCC toolchain to run on your computer. And so the reason why I'm sending you to this site is they've done a nice job teasing that out. So it's most applicable if you're on a Mac. But whether you're Mac or Windows, go to that site, follow that to install your toolchain. And then the rest of this, I won't read it. You've got it here. It's also posted, and the details are all given. But that'll be due 2 weeks from yesterday. And this project involves blinking LEDs and some switches. And it's just to get you familiar with this GPIO stuff. Okay. Okay. Let's talk about kits. The kits are ready. You're going to go get them now. This is just a breakdown of what's in the kit. When you get your kit, open it up, see what's inside it. if you're missing something, then you can go into the lab and pick up the missing pieces at the end of the week. Getting these kits ready, between this class and 300 and 304, we had to make 287 kits. And our vendor flaked out on us and didn't send us the kits. They sent us thousands of parts. So we had to package them all up over the past week. And it's not a perfect process. If it turns out you're missing something in the kit, you can go up to the lab and get it. But for now, I want you to go. David Boucher is going to take you up to the lab now. There are more than 100 of you that are going to go do this, right? There are 150 in the class. But here's what I want you to do. Go with Dave, walk into the lab, enter in the door, proceed down, pick up a kit, and then walk out the east door, right? Grab one of these kits and you're on your way. The whole thing should take 5-10 minutes.